I'm gonna have you do a program for one joint, and I expect you to apply that for the n joints. So first we'll do a cubic polynomial, and then I'll give you a sheet so that you can extend that to a quintic polynomial. So first we'll do q of t. This is your cubic trajectory. Right? So q of t is a naught, a1 t, a2 t squared plus a3. Right? We try to find out the linear system like this. We'll say 1 t naught is your initial time. Then we have t naught squared, t naught cube, 0, 1, 2 t naught. Okay, then we have 1 tf squared, tf cube. You have 0, 1, 2 tf, and 3 tf squared. This is your coefficient matrix for this. And then you have the set of variables that you're trying to find out. A0, A1, A2, A3. This will be equal to the initial and final parts, which is Q0, V0, QF, right? From here we'll find out what is A0. So let's call this, as we decided, this is your T matrix, this is A, and this is K, right? So we can find A will be equal to T inverse times K. Okay? So let's set this up for a single joint. We'll look at the acceleration and velocity profiles. We'll see if it reaches the initial and final positions in the given time as we expect it to do. If not, we'll check it out. Okay, so let's create a new one, new script here. And let me pop this out. Okay, so the first thing I want to do is we'll do it for a single joint. Okay, so I'm going to say Q0, Q0 for a single joint is, let's say we start from 30 degrees. All right, I'm just going to call this as 30. I'm going to put it in a matrix form in case we need to add more later, more joints later. This is your initial position. Okay.
Professor,
Probably need to increase the font.
Can you please increase the font?
Sure.
Yeah.
Is that better?
Yeah, thank you.
All right. So all right. So let's do the final position, which is QF. Let's go to 90 degrees, for example. And this is my final position. Same thing with velocity, we'll call V0. I'm going to say it is 1 radian per second. Okay, initial velocity, if you want, you can do starting from rest. If I want starting from rest, I'll go with 0. All right, let's take this one example as starting from rest. This is, okay, final velocity, we won't stop at rest, but we'll have a velocity like this, which is a negative velocity. That means it is decelerating or accelerating in the opposite direction. So this is your final velocity. All right. Now we want to set up the T matrix here. Once we set up the T matrix, we should be able to view this. So what I'm going to do is I'm going to say capital T is equal to we'll go row by row, so it is, we need to write the times, right? So let's go to set up T0, T0, okay? T0 can be 0 or it can be anything. So let's say that in this example, I'm starting at T equal to 0 seconds. This is the starting time. And I don't want to do a problem with unit time. Unit time is pretty simple, so we'll go and set it up as 3 seconds, okay? I'm not gonna do a unit time motion, but you can change it to 1 to test it out. So this is stop time. All right? So let me set up this first row. So T, let's go say this is 1, T0, right? Yeah, T0, then we have T0 square, okay, and then we have T0 cube. This is the first row of the T matrix. Okay. And then I can go here, 0, we have 1, we have 2 times T0, right? And then we have 3 times T0 squared. The 3 dots mean that it is continued in the next line, okay? It's not necessary that you put the 3 dots at the end of the semicolon, but it just means that it is continued over the next line. Whatever statement you are giving is continued over the next line, okay? Same way, we'll repeat this for TF. So this is TF, TF square, TF. And finally, 0, 1, 2 times TF, 3 TF square.
Professor, in the second one, it's a 3 plus instead of 3 minus.
Yeah, 3 times. Thank you, sir. Thank you. 3 times. Thank you. Okay, so we can close the parenthesis here. All right.
The second one should multiply T.
Second line should be what?
Multiply T and F. Or you can just use.
I don't understand. What's your question?
Third line, we have to multiply T and F.
T and F. TF is a single variable. There is no T and F. TF is a final term. There is no.
Yeah.
Professor, what about these 3 dots or 3 points?
It means that, okay, so when I'm trying to write a statement, right? When I'm trying to write a statement, let's say that I want to continue from here over the next line. I can just put 3 dots in between and write the rest of it on the next line. That means this statement is continued in the next line, okay? Alright. Now, let's have a look. Let's look at what T looks like. So I'm just gonna save this as, let's say, cubic. Okay, cubic 1, because it's a single joint. I'm gonna use it like that. Let's go here, save this, and let me run it. Okay, so this is your matrix. All right. Now what I'm going to do here is, let's suppress the output there. Now, the next thing is to find A. So A will be equal to inverse of T. T inverse, we write it as the inverse matrix in MATLAB. If you want to compute the inverse of a matrix, you just write INV. That is the inverse. So I can do that here. For example, I can check it out here. So I can say inverse of T. So it will give me the matrix inverse like that, okay? If you want, we can go to the command window and check out the inverse command. Okay, times, we need to set up a matrix, which is this, right? Q naught, V naught, QF, VF. So what we'll do here is we'll basically say this will be equal to Q naught, V naught, QF, VF, and this has to be a column matrix. So I'm going to do it like this. Okay, make it a column matrix like that. So when I do that, I should have the 4 coefficients within A, right? I should have the 4 coefficients within A. So let's check if I get A here. Q naught. All right.
Q0.
Yeah.
QO.
So we'll replace that. B0. All right. Okay. So as we know that Q naught is, A naught is Q naught. When we solved that, we saw that A naught was Q naught. So we are starting at 30, it has 30. A1 was 0. So A1 is again 0 like we did. Theoretically, A1 turns out to be 0. And your initial displacement, because when t is equals to 0, all this is 0. When time t is equals to 0, all this is 0 because you're multiplying with t. Therefore, A naught should be equal to Q naught, the initial position of the joint. So initial position in our case is 30, so A naught turns out to be 30 degrees. Okay, now let's try to plot the profiles. So from here, I'll just say that okay, so we'll say from here, A0 will be, let me try something, give me 1 second. Just yeah, it's not gonna work. Okay, anyways, so we'll do it like this. This is your A naught, same way. A1 is going to be A of 1. These are the 4 coefficients. Now to plot it, let's create a timeline. To create a timeline, there are different ways you can do it. What I'm going to say is t, which is time, small t is a variable we haven't used. I'll say 1 to t, to 100 tf. Okay, what does this mean? Actually, let's do it like this. T naught, T0, 100, TF. That means between T naught to TF, it will take 100 points. Okay? So it will divide the interval between T naught to TF. So when I do evaluate here, let's evaluate this. You will come up with 100 points. It's only coming up with 0. Let me do it like this. Okay, this came up with 0, it should stop at, or let me try this. Okay, let's go with line space, because it will divide this into linearly. So you have 100 points between T0 to TF, so we can plot the velocity and acceleration and all the profiles in one line. Okay. All right. So if I want to compute Q, I can put a for loop to calculate use this formula to calculate the trajectory for each value of t. If I don't want to do that, if I want to compute the whole array at one go, this is what I'll do. I'll do a scalar multiplication. So what we'll do is we'll say Q, have we used Q somewhere? No. Okay, so Q will be equal to A naught, all right, plus A1 dot T. Actually, let's do, this is A, you can do it like this, okay, plus A2, it's a scalar, okay, this will be this, and then T. Okay, that means T times T is element-wise multiplication, okay? If I remove the dot between that, it becomes a normal multiplication. This is a scalar multiplication. So if you're multiplying, let's say, these two matrices, it will multiply A naught with Q naught, A1 with V naught, so element-wise element multiplication, okay? So let's go here, plus A3 okay. Let me check this out for 1 second. All right. So we'll get a row matrix, not a column matrix, which is fine. So once we have this, you'll have a trajectory for Q, like that, and we can plot this on a timeline. So let's go here, and I'll say, X is your time, Q is the y-axis. Okay, if you want, you can title it. All right. Okay, so when you plot this, you'll see, if you want to see a grid line, just type in grid here. So it starts from 30 and it will go up to a maximum of 90 degrees, like that. Alright, to this, let's add another plot, another couple of plots. The second one is your joint velocity and joint acceleration, right? So let's calculate V. V should be equal to A naught is 0, you have A1 plus 2 times A2 right, plus 3 times t squared. Okay, this will be your velocity. So you can have a second plot. So let's run this and you, yeah,
For the velocity, I think we should add more A3, the last one.
yeah, A3, you're right. Thank you. Okay, so here you can see that the velocity starts at 0, it ends at -1. Okay, so you're starting from rest here. It starts at velocity 0, but it ends little below than the 0 line. Okay, so you can compare the two like that. So this one is perfectly fine. It starts from 30, stops at 90. It's a cubic trajectory. It'll slowly start moving, and then it has maximum speed here, and then it'll stop here. So same goes here. This is the maximum velocity in between, and then it will come to rest. Actually, it does not have a final resting velocity, but it has starting 0 velocity and stopping at -1. Okay, so you can change this to anything you want. Let's say I want to go here and I change this to a final velocity of 0. So it's starting at rest, stopping at rest. Now I can check my plot. Starts from 0, stops at 0 in 3 seconds. If I want to make this 5 seconds, I'll just change my stopping time here to 5 seconds. And then it will stop in 5 seconds, okay? So you can change that any way you like. Now let's do one thing. Here, what I'm gonna say is, let's plot the acceleration also. All right, so when we do the acceleration, it's differentiating this once again with time. So this will be 2 times A2 plus 6 times A3 times T. Okay, I made a mistake. This should be A. Okay, so you can see that this is a unstable system because you're starting with a very high acceleration and you're stopping with a very high acceleration. Okay, so this will create vibrations in the system because you're not smoothly stopping, you're just coming to an abrupt stop. Okay, so all right. Now, this is pretty much straightforward. What I want to do here is in this code, there are 2 things I want to do. So I'm gonna show you how you can change this. So let's say you want to convert this into a 3-joint manipulator, right? Let's say you have 3 joints, not just 1 joint, but you have 3 joints. You're talking about a 3 degree of freedom manipulator. So instead of 1 joint here, this could have 3 joints here. So this could be the first joint is 30 degrees, second joint you're starting from 0, and the third joint, let's say you're starting from -20, right? If it's a 3 degree of freedom manipulator, we'll have 3 joints. So what you want to do is we'll modify this code to include not just 1 but 3 joints. So I'm just gonna copy this and create another program so that we don't here. Okay, let's have, I'm gonna save this as cubic 3.
Professor, can we have a second just copying the previous one?
Absolutely. Take your time. When is your final difference?
December 7th.
What was the lens space actually?
Lin space means linearly spaced variable. That means if you give it a starting and stopping value, it will divide it into equal intervals, linearly spaced. That means they are spaced equally apart. So if you give 100, that means 100 points equally spaced between starting and finish. If you give it as 50, there will be 50 equally spaced points. So it's linearly spaced. It's a straight line between Q0 and QF.
What's the difference between T0, 100, PM? Did I do this before?
That is a linear count. It will work like this. It does not work when you have decimals. So for example here, right? If I do T is equals to 1 to 5. It will work like this. It doesn't work if I give it like this. The last one is not 0.6, right? It does not stop at, so it's not linearly spaced.
Okay.
Okay, it's in integer values.
Okay.
All right, are we good?
Yeah.
Okay, fine. So let's have this simultaneously do this instead of, if I give you a set of joints, let's say you have a 3 degree of freedom manipulator, so you have 3 starting positions for each of the joints. Same thing for stopping, right? So for example, how do we change this to make sure that all of them we can compute in one go instead of doing this again and again? Alternatively, you can write it as a function and you can call the function for 3 joints, right? You can make this into a cubic function where you send in Q0, QF, V0, VF, and the starting time and the final time, and it will return you the trajectory. You can do that, or you can do what I'm doing, which is completely up to you, doesn't matter how you want to do it. Okay, so let's say that I have this, let's say 10, and I have 60 degrees, right? Here it's 0, I want 50, all right? And let's say we are starting all the joints from rest and we are coming to rest. Okay, let's not complicate this too much. And once we get this, we can always come back and change the values, all right? Starting time and stopping time is the same for all the joints. Okay. So long as the start time and the stop time is the same, this matrix remains the same for all the joints, the coefficient matrix. Only thing that will change is this. So if I'm doing first joint, this will be different. If I'm doing the second joint, this will be different, and so on. Okay? So I have 3 joints. So let's basically understand the problem before we code it so that it's simpler to do that way. Okay, so when I'm using the first joint, all of this will be of 1, 1, 1, 1, right? Because every joint, let's say I have a 3DOF manipulator. For the Q1, for the first joint, I'll have its own set of coefficients and a trajectory. Q2 will have its own trajectory, therefore it has its own set of coefficients. Same thing with Q3. So for each of the joints, you have to find A0, A1, A2, A3 that define the trajectory, right? So this matrix remains the same because your start time and stop time is the same for all the joints. So this is common to all the joints, same for all the joints. Okay. So if you're talking about the first joint starting value, first joint velocity, first joint stopping value, first joint stop velocity. Then we have to compute this for the second joint. Then you have to compute the trajectory for the third joint and so on. Okay. So what we'll do is we'll nest it in a loop and we'll try to find them out in one go here. So once you have found this out, let's go here. I'm going to say A is equal to like this. Okay. So what I'm going to do is I'm going to create a coefficient matrix like this. A coefficient matrix will be like this. A0, A1, A2, A3. This is for the first joint. A0, A1, A2, A3 for the second joint. A0, A1, A2, A3 for the third joint. This is for Q1, Q2, Q3. Okay? So we'll simultaneously put all of them together here. So let's say we go here and say for n is equal to 1. In our case, it's 3, so I'm just going to write it as, okay, you can have this as NDO or whatever. So here, we'll have to take this and say I'm going to call it as a temporary variable. Let's call it as temporary variable like this. Okay. So here I'm getting a column matrix. So this first column, if I want to relate this to the first joint, then it has to be Q0 of 1 because Q0 of n. First joint, second joint, this is and we'll concatenate it like this. Let me comment this here. We can test it out first before we plot anything. Okay, there's nothing in A, which is amazing. Let's